One. All right. All right. Hi, everyone. Oh, so I want to recap what we've done for the past couple of times, and then we'll move forward to a new topic. So again, like when we're asking for the asymptotic worst case runtime complexity of the function f for input of size n, what we mean is basically for large n, what is the runtime proportional to of f of n? So the reason we are asking it like that is because in general, like you have like two computers, so you have like computer 1 and you have computer 2, and this one is whatever C1 operations per second, and this one is C2 operations per second. Then what's gonna happen is if the complexity is G of n, then this basically the runtime is going to be G of n divided by C1 for computer 1, and the runtime is going to be G of n divided by C2 for C2, assuming this is number of operations. Something like this, right? So in either case, the runtime is going to be proportional to G of n, but it's going to be divided by C1 in this case, divided by C2 in this case, and we won't necessarily know what C1 and C2 are ahead of time, right? But we can say, well, like G of n gives us an idea of how fast or slow the runtime is going to grow when n becomes very large. So worst case just means that if the input is of size n, it might be that for different inputs that are both of size n, the runtime is going to be different. And we're saying, find me when the input is still of size n, what's the worst it can get? Right? So the kind of easiest case that you could have is something like this. So if you say like for I in range K1 and then for J in range K2, and you have something like this, then you could say this is O of K1 times K2. Why? Well, because this repeats a constant number of times. This takes a constant amount of time, and it repeats K1 times K2 times, right? So this would be O of K1 times K2. So this would be more familiar maybe if you thought about it like this. So if this is like n and this is like 2 times n, and this is some block of code, then ordinarily you would just look at it and say, oh, this is O of n squared, because the runtime is proportional to n times 2n, which is proportional to n squared. All right. So the most usual situation where this doesn't work is if the block does not run. So how can the block not run in a constant number of time? Block not run. Well, this would be if the block, the runtime depends on n for the block. So maybe the block is something itself like for m in range n, whatever. Well, the runtime of this is proportional to n. It's not constant. If n is larger, then this is larger as well. Of course, usually this would be represented as a loop within a loop within a loop. But a block can also be a function call or something where the loop is hidden. So something like this. Or it could be the block is like sum of L, where L is of length n. Or it could be something like the block contains an integer operation or an integer that grows larger and larger. Right? So the example that you might imagine is like something like this, and then you're saying while, or like for I in range n, res is equal to res squared. So here it looks like this repeats n times, so you might say it's O of n, but really it's not, because if res gets very, very large, which it can if it's an integer, because integers are unlimited, then multiplying two numbers which have like 1 billion digits each by each other, that would take longer than multiplying small integers by each other. So this doesn't really take the same amount of time for every iteration, so that's not constant time. So those things usually are difficult to analyze, things involving integer operations. So for that reason, if you look at past exams, like everything is a float operations, because float operations do take constant time. Because floats are limited, they have a limited number of digits. Okay. So that's kind of just loops. So the other things that we saw were things like this. So we had a situation where we had for something, and then we had a block. Where the block takes different number of times to complete each time, but we kind of can figure out that k1 plus k2 and so on plus kn is just equal to n. And that was the situation with counting sort, where we had this idea of you're building up the result, and the result eventually is going to be of length n. And we don't know how many operations each extend is going to take, but we know that in total, we keep extending the result until it's of length n. So we know that eventually we're extending the result by n elements. So that takes time that's proportional to n. So that block, so this is, you can just go and look back for counting sort, that was like res.extend I times count size, something like this. And we said, well, like, we don't know how many times each iteration, how many operations each iteration is, but we know that in total the result will have been extended by n elements. So the sum we know. So that was a tricky kind of analysis. So another situation where it was kind of tricky was when we were doing the analysis for bubble sort, right? So in the analysis for bubble sort, it was kind of like this. So it was like for something, for I in range n, in fact. And then here we had for another thing, and then this was constant, and this we said runs for n, and then n minus 1, and then n minus 2, and so on down to 1 times. And for this, we just figured out, okay, the total amount of times that this runs is 1 plus 2 plus 3 and so on plus n, and for that we had a 4. Right, and that's the only formula. There will be one more, but for now, that was the only formula that we really needed in order to figure those kinds of things out. It's the formula for the arithmetic series. Okay, and the calculation was in total the block. So to be clear, this is the block. In this case, which is equal to n plus 1 over 2 in this kind of example. The other situation, and that was the analysis for binary search, the situation basically looked like this. It was slightly more complicated, but basically it looks like this. So we said, like, while n is greater than 1, just divide n by 2. So how many times does this run? Well, you start with n, and then you go to n over 2, and then n over 4, and so on until you get to the bottom. And you could say, well, like 1 is 2 to the 0, and then 2 is 2 to the 1, and so on. And eventually you'll get to 2 to the k. And that's k steps, right? Because k minus 1, and so on down to 0. So basically what is k is the same as how many steps from n to 1 divided by 2 every time. And here you can just say, well, like n is equal to 2 to the k, and that means that log 2n is equal to log 2 to the k. And that means that log 2n is equal to k because log 2 to the k is just k. So to get down from n to 1, going in steps of divide by 2 every time is log 2n steps. And then if every operation here took a constant amount of time, well, this runs for log 2n steps. So that's O of log 2n. So the reason I did this recap, I think it was like maybe too quick. Like if you didn't study, that was maybe too quick. But we've done each of those examples before. And the point is, if you look at the exam questions, like they're all like that because in general, it can be very difficult to determine the complexity, right? And sometimes it's a research problem. Sometimes it's an open research problem. So just like on a calculus exam, like if you're given an integral, well, like there's probably a trick to do it that you've probably seen in class. Here as well, like unless sometimes there's a problem solving question where I kind of want you to do kind of one step beyond what's done in class, but most of the time, it's going to be one of those tricks or a combination of those tricks. So your job is to basically look, we'll have a few more in the few classes that are left, but basically your job is like to look at the question and say, okay, like what is the trick or the combination of the tricks that I can use? out of what I listed and what will be in the next few coming lectures that I can use in order to figure out what the complexity is. Make sense? All right. So and like the point is it's a finite number of tricks. Like it's not very many. So just go through the examples that we've done, identify, okay, like this is the trick that was used. Maybe think of, okay, like this is one more example where it would be kind of similar, and you should be pretty much set. So, okay. So one thing that I haven't gone into here yet is kind of worst case versus best case. So usually the worst case is the same as the typical case. So sometimes you'll have situations where, you know, like the worst case, for example, in bubble sort, you maybe need to think about it a little bit about like what exactly is the worst case there. If you remember, the worst case was if the smallest element is at the very end, then you need all the iterations to get the smallest element back to the very left of the list. So, okay. Questions about this? All right. I want to start. So we'll come back to complexity when we analyze the complexity of the recursive functions. But for now, I want to start what's a new topic, and that's recursion. So functions using themselves as helper functions. So I'll start with kind of an example, and then we'll move on from there. So n factorial, as we've mentioned in the last lecture, is this kind of product. And one way to compute it is by realizing, okay, like n factorial is 1 times 2 and so on times n minus 1 times n. So that's n minus 1 factorial times n, right? Because this part is n minus 1 factorial. It's 1 times 2 and so on up to n minus 1. So we can write it in Python this way. So I'm saying, what's factorial of n? Well, it's n times factorial n minus 1. So we'll need what's called a base case as well. So we'll say if n is equal to 0, we'll return 1. And that will do it. So one way to think about it is using this kind of, so this is what's called leap of faith. If factorial of n works for small n, it must work for large n as well. Right? So another way of putting it is like, if factorial of n works according to its docstring, it says return the factorial of n, then, well, it must work because it's true mathematically that n factorial is n times n minus 1 factorial. And according to the docstring, the function works, and I used the function in the correct way. So it must be that for a large n, it's going to work out, because for smaller n, it also works out. Okay. So another way of thinking about it is, okay, here is how it would actually compute. So what I'm going to do now is draw what's called a call tree. So a graphical representation of how the computation of fact proceeds. So let's say that's say fact 4. So fact 4, so here I'm saying n is not equal to 0, so I'm going to return 4 times fact 3. So I need to compute fact3. So I'll represent it this way. I'll say I need to compute fact3. And now when I'm computing fact3, well, I need to compute fact2. So that'll call fact2. And that'll call fact1. And that'll call fact0. Now, fact0, there's nothing complicated about it because it just says return 1. So here, that'll return 1. So now that we know that fact0 returns 1, well, fact1 returns 1 times fact0. Fact0 we already know is 1. So it'll return 1 times 1. So fact2 returns 2 times fact1, and fact1 is 1 because we already know. So that means that fact2 is going to return 1 times 1 times 2. And fact3 is going to be 3 times fact2. Fact2 is 1 times 1 times 2, so that's 1 times 1 times 2 times 3. So that means that fact4 is which is 4 factorial because it's 2 times 3 times 4. Okay. So in general, what you want is you want some kind of formula that uses an input that's in some sense simpler. So here, like we're getting n to be smaller and smaller until eventually for n equals 0, we just know the answer. And you want what's called the base case. So that's what's the output for a very simple answer. Right? So you might say, so you can't push on a rope, you need a base case. So if you didn't have if n equals to 0, then you would go to n minus 2 minus 1, minus 2 minus 3, and so on to infinity. And you need a recursive step. I don't know if that's funny anymore, but okay. And also f equals ma. So okay. So anyway, so those are kind of the two things that you need. Okay. So why do you need the base case? Well, because if you didn't have this, then you would be trying factorial n minus 1, minus 1, minus 2, minus 3, and so on. That doesn't even make sense. And then here you need, and we'll see kind of later on when this becomes kind of less trivial in terms of figuring out what does it mean to have a call that's in some sense simpler. But here we just keep making the n smaller until it becomes 0, and then we know the answer. Okay. So let's do another example. Let's say that I want to print the list L. And without print L. And without loops. So basically, I want to print like L at 0, L at 1, L at 2, but I don't want to use a loop. And I don't just want to say print L. So need a base case and need a recursive step. So the base case is if the list is of length 1, just print L at 0. The recursive step is we need to simplify the problem somehow. And one way to simplify the problem is print L at 0 and then print the rest of the list. So I'll write the docstring. And I'll first do my base case. So I'll say if the length of L is 1, just print L at 0 and I'm done. And now I'm saying, okay, if I'm here, that means that the length of the list is not 1. So what I'll first do is I'll print L at 0, like the recursive step says. And then I'll just print the rest of the list. Like so. Okay. Why does it work? Well, one way to think about it is leap of faith. If I print the first element and then I print the rest of the list with a function that, according to its docstring, actually works, that means it's got to work. So the other way is to, again, do a call tree. So let's say that we start with the list 5, 6, 7. So what happens? So we're here, we're saying print L at 0. So that means that 5 gets printed. And then we call print list with the rest of the list. So with 6, 7. So at this point, what happens? We print L at 0, so print 6, and then call print list with the list 7. And at this point, we just print 7 and we return. So that would print 5 and then 6 and then 7. And we have our base case, which is, in this case, the output for a very simple case, which is just the list being equal, the length being equal to 1. So let's solve a very similar problem. So let's say that I want to say print the list L in reverse. So there's several ways of doing this, just like with this, but I want to pick a particular way. So the base case is going to be the same, right? So if the list is of length 1, then the list in reverse is the same as the list. You just print L at 0. So the recursive step might be print the rest of the list in reverse. And then print L at 0. That would work, right? So like if you're thinking about 5, 6, 7, you can say, well, like to reverse it, it's going to be 5 at the very end. And then what comes before 5? Well, it's like the reverse of 6, 7. Make sense? So, okay. So let's do the base case. So the base case is exactly the same. And here we'll say, okay, so we're going to print the rest of the list in reverse. So that's going to be like this. And then we're going to print L at 0. right? That's what we said, right? So first print the list in reverse, or the rest of it, and then print the first element. So let's see how that's going to work with an example list. So we call it with 5, 6, 7. We get to here. So print reverse 6, 7. We get to here. Print reverse just 7. When you call just the list 7, it'll print 7 because the length is 1. So when you call 6, 7, what's going to happen? Well, first it's going to print 7, and then it's going to print the first element, which is 6. So it's going to print, after it's done calling print reverse in just this list and printing 7, it'll print 6. Here, what's going to happen is it's going to print reverse this. So it's going to print 7 and then 6. So that will print 7, 6. And then it'll print 5. So what you'll notice is that those call trees are exactly the same. So the difference is the chronological order. Here, when I called print list, it first printed 5. So it printed 5 right away, and then it called print list on 6, 7. Here, what happened is it called print reverse on 6, 7. And then eventually that will have printed 7, 6, and then it printed 5. Right? And that's just because it waits for this to finish. So it waits for print reverse 6, 7 to finish running. And then it prints L0. So 5 gets printed at the end. Make sense? So here, I kind of like made it so that it kind of works out this way nicely. But the effect of basically reversing those two lines was that before we were printing the list forward, and then we were printing it backwards. So again, another way of thinking about what this was doing is print reverse, assume it works, assume it prints the list L in reverse. Well, it says print reverse 6, 7, so that'll print 7, 6, and then it prints 5 after it printed 6, 7 in reverse. Here, what it's doing is it first prints the first element, and then it prints the rest. So naturally, that would change the order. Because if you print L at 0 at the end, it will be at the very end. If you print L at 0 in the beginning and then you do everything, then L at 0 will be in the beginning. And similarly, like, okay, L at 0, maybe it's at the start, maybe it's at the end, and then think about what this call does. Well, it prints the rest of the list. So the rest of the list here is just printed forward. Here, when you're saying print reverse the rest of the list, well, what does it do? Well, it'll print L at 1 at the very end. All right. So that's kind of thinking about it the way I just described involves just basically kind of like internalizing the entire call tree, which might be challenging at first. So one thing you might do instead is you might just think about this, right? So it is really the case that in order to print the list in reverse, what you need to do is you need to print in reverse the rest of the list and then print the first element. Like that's what it means to print in reverse. And that's kind of another way of thinking about why this works. Make sense? All right, let's do another example. Let's say that I want to compute a to the n. So one way of thinking about what a to the n is you could say, well, mathematically, a to the n is equal to a times a to the power of n minus 1. That's just true about powers. So that means that you can write it like this. Right? So this is just this. Now, you also need a base case, because if you don't have a base case, then you're going to be trying to compute like a to the minus 1 and to the minus 1 million and so on. You could say, okay, if n is equal to 0, just return 1 because a to the 0 is 1. All right. So again, you need a base case and you need a recursive step. Questions? So I want to start talking about other ways of computing it. So you can do something like this, right? So you can say like result is 1, and you could say for I in range n, result times a. So that would also be a to the n, because you're multiplying a by itself n times. Right? So I want to first transform it into, sorry. So I want to first transform it into a while loop. So the way I'll do it is, so here I go 0, 1, 2, 3, and so on up to n minus 1. So I'll just do it explicitly. I'll say I is equal to 0. And I'll say while I is smaller than n. Like this. So that's like clearly the same thing, right? And then it turns out that this gives me the possibility of rewriting this without using loops. So what happens here? Well, I start with result being 1 and I being 0 and n is just n always. And then result changes. I multiply it by a every time. And I changes at 1 every time. Right? So that's the structure here. That's the while. I add 1 to I every time, and I multiply result by a every time. So that allows me to write it like this. So I'll write it and then I'll explain it. So what I'm doing here is I've plugged in a and n and result in I, and I'm saying here when I is equal to n, I'm done. Result is already what it was gonna be. I just return it. And here I'm saying if I plug in I that's equal to n, I'll just return result. And then here I'm saying put a into a, so don't change that. Put n into n, so don't change that. And then put result times a into result, and put I plus 1 into I. So in effect, I'm doing the same thing here, right? I'm saying keep going while I is not n. And then keep putting result times a into result and keep putting I into I plus 1 into I. Right? So this is this. And then this is this. So the way this would go is I start with a and n and 1 and 0 if I put 1 into result initially and 0 into I initially. And then that would become a and n and a and 1. And then that would become a and n and a squared and 2. And so on. Until eventually that will be a and n and a to the n and n. And then from here, I'll just return a to the n. Because once I is equal to n, I return a to the n. And then here, I just keep returning. And so on down to just returning a to the n. So we'll do it in more detail on Wednesday, I think, because there is not time now. So in particular, the difficult part is why does it keep returning a to the n down? Well, it's because we're just saying return this. So like once it's done the computation, it'll just return whatever was the result for this call, right? So we're not so unlike above, where we're returning a times power whatever, like we're returning a different thing every time, here we're returning the same thing every time. Right? And here, so like we return res eventually, and that means that when you're calling it from a to the n minus 1 and minus 1, well, the upper call returned a minus n, and then you just return whatever this returned. Right? So that's kind of like this. Again, we'll come back to this on Wednesday. One thing to note here is that the structure of the computation is not really the same, right? So if you think about the computation here is up the call tree, you keep changing the n, and then down the call tree, you keep multiplying by 8. Over here, you just go up the call tree, and then you just you're just compute a different thing up the call tree. So this is 1, and then a squared, and so on. But down the call tree, you just return a to the n. So that should not make complete sense now, but it hopefully will on Wednesday. Questions? Yeah. Say it. A to the power of n. All right. So let's try to do this, and let's try to do this in a little bit more detail. So here, what's going on? So we start by calling a to the power of, let's say, 5. And then this calls a to the power of 4. And then this calls a to the power of 3, and so on, until it calls a to the power of 0. A to the power of 0 returns 1. So that means that a to the power of 1 returns a times power a0. So that returns 1 times a. So that means that eventually this will return 1 times a times a times a times a. And that will return this times a. So a to the power of 5. Here, what we're doing is we're calling AN10. And then that calls this because we call it with 1 times a. So this becomes a. And then from here, we call this. So this becomes a squared and so on up until the point where we get to a to the n. And at this point, you just return this. Yeah. Well, like if you call it like this, then it would be. So that we will have to set up on Wednesday. Yes. Yeah. We do go back down, right? So like what happened, it's just that here you're just saying return whatever this computed, right? So this means that once you start returning, you're returning the same thing every time. Right? So over here, it would look kind of like this. And here you would call this guy, and this guy returns a to the n. So this means that this guy also returns a to the n because you're just saying return whatever the call above you returned. All right. More on this on Wednesday, and there's going to be a recursion lab, or partially a recursion lab on Wednesday, Thursday. So hopefully you'll get some practice with that. Although it's technically optional. Well, I mean, like I said, so like because the syllabus said it's 9 labs, really it should have said 10. That was like a mistake. So you're graded a 9. You can treat those as exercises, and there's going to be more exercises anyway for kind of the material from the last several weeks. So that's going to be posted in the next few days. Yeah, I'll see you Wednesday. Bye.